Well, we've seen how to add and subtract vectors graphically, and now it's time to look at the other method for doing it, which is more practical. You'll be using it much more often. In fact, if you move on and take electricity and magnetism, much of the material in the first half of that semester is going to involve a lot of vector manipulation. So it's good to get it down now here in mechanics. Here's a vector A, which has been resolved into components along the x and y axes. And now let's give this angle a special label, theta sub A, where the letter here refers to the vector that you're talking about, because soon we'll be adding vectors, 2 or 3 vectors at a time, and if we've got labels like A, B, and C, then we'd like to distinguish the various angles as well. Now you'll notice that this angle has been measured from the positive x-axis. And that is the convention that will usually follow, not always, but typically the angle that we assign to a vector will be an angle measured from the positive x-axis. And if the angle is swept out counterclockwise, we consider that to be a positive angle, just like you may have learned in pre-calculus back in high school. So this angle would be considered a positive angle. This angle has been swept out clockwise from the positive x-axis, and we consider that to be a negative angle. So I'm just going to estimate this angle at something like negative 25 degrees. Now you may be aware, you could also locate this vector by measuring a positive angle that sweeps all the way out to here. So if this is, what did I say, 25, 360 minus 25, I think that's 335. So you could either say that this vector is at positive 335, or you could say it's at negative 25. Those are equivalent. So I used this slide in a previous video. We all know about the sine, cosine, and tangent functions. Sine and cosine we'll be using very often, and it's useful to think of these ratios in this form. Again, if you know the hypotenuse of a triangle and you'd like to know the length of the side opposite to this angle theta, well, the opposite side is just the hypotenuse times the sine of theta. Similarly, the adjacent side would just be the hypotenuse times the cosine of theta. You really want to memorize that because it'll save you some time. Also, you may have heard, not SOHCAHTOA, ASTC. Some people like to say add sugar to coffee, if that helps you remember it. There's a variety of mnemonic devices that you can look up that will help you remember that. The purpose here is to remind you that of the 3 functions, sine, cosine, and tangent, all 3 of them have positive values or take on positive values in the first quadrant. So if you're talking about an angle between 0 and 90, the sine of that angle, the cosine of that angle, and the tangent of that angle are all positive. This one tells you that the only function of those 3 which takes on positive values in the second quadrant would be the sine function. So the fact that it says sine tells you that cosine and tangent take on negative values for angles between 90 and 180. So these are just basic trig facts that you really want to memorize because you use them so often in this class. You don't want to be hung up reviewing your trig every time. So this is a good time here at the beginning of the semester to rehash all this stuff and feel confident about it. In quadrant 3, the only function of those 3 functions which takes on positive values is the tangent function. And that's because down here, the x-coordinate of a point and the y-coordinate are negative. So when we take the ratio of 2 negative numbers, we get a positive number. And in quadrant 4, the only function of those 3 that's positive or takes on positive values would be the cosine function. So ASTC, if that helps you. This graphic is just to help you visualize the fact that the sine function takes on positive values in both quadrants, which are above the x-axis, and it takes on negative values in both quadrants, which are below the x-axis. And the reason for that, remember the sine function, if this is my angle theta here, I haven't labeled it, but suppose this is theta. The sine of theta is the opposite side divided by the hypotenuse, but you have to take into account the sine of the y-coordinate. Think about it. The length of this side here would be the y-coordinate of this point. And whether you're here or here, that y-coordinate takes on positive values. But if you're If your angle was all the way over here, you'd have a y-coordinate that's negative, and that's why your sine function would come out negative. Cosine is different. Cosine is positive in these two quadrants. Remember, the cosine of this angle would be the adjacent side divided by the hypotenuse, but we do include the sine, S-I-G-N, of this side. So if you can see that for this point right here, the x-coordinate would be the length of this side. But over here, that x-coordinate is negative. And when you take the negative number divided by the positive hypotenuse, you should get a negative number. So you want to memorize both of those pictures. Here's an angle or a vector for which the angle, the conventional angle, remember the angle that the vector makes with the positive x-axis, in this case, is an angle in quadrant 2. So if we go to compute the sine of this angle, we will be taking the sine of an angle in quadrant 2. The sine function is still positive in that quadrant. Now, if this is theta A, then the angle inside the triangle here must be the so-called supplement, or 180 minus theta A. Here I've written pi radians minus theta A. So now let's use our rules about calculating the opposite and adjacent sides using, I think I'm okay. Using this triangle here. So if we're interested in the y component of this vector, first of all, let's note the y component is a positive component. See how this vector with the arrow plus this vector has a sum equal to this vector. That's the graphical addition of vectors. So we know that this component is positive because it points upwards in the direction of the positive y-axis. So whatever we do with the trig, we know that we need a quantity that has a positive sign. So down here, I take the length of the hypotenuse and I multiply by the sine of this angle, the sine of pi minus theta A, to get the positive y component. But there's a trig identity that you're probably aware of. If you take the sine of 180 minus an angle, that's the same as the sine of that angle. So sine of 180 minus x is the sine of x. That's a trig identity you should know. Yeah, and let me emphasize that before I move on to the next slide. Look at the far left and the far right here. This is going to be the expression for the y component of any vector that you can always use, provided that you measure the angle theta A the conventional way. So you want to commit that to memory. The y component of your vector is given by a sine theta, where theta is the angle that the vector makes with the positive x-axis. That will always work. That will always give you the correct y component of your vector. What about the x component? Well, this time, because the x component points in the negative x direction, we are going to need a minus sign in front. But using our rule for the adjacent side of a triangle, if we take the hypotenuse, which is A, and you'll notice I haven't written the arrow symbol here. I could have, which just indicates that it's a vector quantity. Without the arrow, A refers to the length or magnitude of the vector A. So take the magnitude of vector A, which is the hypotenuse of this triangle, and multiply by the cosine of this interior angle to get the length of this component. But then we have to add the minus sign because we know that it points in the negative direction. So we're accounting for the direction here. Now we invoke another trig identity. If you take the cosine of 180 minus an angle, you pick up another minus sign. So the cosine of 180 minus theta is actually negative cosine of theta. Those two minus signs will cancel and we're left with this expression. So this is another formula that you want to commit to memory. You can always calculate the x component of a vector by taking the magnitude of the vector and multiplying by the cosine of the angle that the vector makes with the positive x-axis. And the nice thing about this formula is it automatically accounts for the sign of your component. The way I derived it here, I looked carefully at the triangle and decided whether the component should get a plus or minus sign. If you do it this way, you don't have to worry about that. You just plug in the angle. Notice, since the angle is in quadrant 2, when we calculate the cosine of that angle, quadrant 2 is a quadrant where cosine is negative. So we automatically get the minus sign that we need to account for the fact that the component points to the left. So as long as you measure your angle from the positive x-axis, you can always use this formula to calculate the x component of a vector. So to summarize, here are the formulas for converting between what you might call polar components or polar coordinates to rectangular components. If you happen to know the length of a vector and the angle that the vector makes with the positive x-axis, these are the two formulas that will convert that length and angle into the so-called rectangular, also known as Cartesian components. Rectangular, Cartesian, those mean the same things in this context. Again, always valid, as long as you measure your angle with respect to the x-axis. Now, I meant to put some slides in here about angles defined differently, other ways of getting the components, but we'll do that when we look at some of the homework problems. So you don't have to use this angle to specify the components of a vector. But if you do use this angle, then these are the formulas that you would go with. Here's another example. This vector has an angle that's in quadrant 3, if we're talking about the angle measured from the positive x-axis. So remember, all students take calculus. That's the other one, besides add sugar to coffee. In the third quadrant, only the tangent function is positive. So both sine and cosine are negative in quadrant 3. So when we evaluate these formulas, we're using an angle for which the cosine function and the sine function take on negative values. That means both of our components will come out negative. Makes sense, because when you look at the picture, you can see the x component points along the negative x-axis and the y component points along the negative y-axis. So these formulas will always work, provided you have measured your angle correctly, or use the convention where theta is measured from the positive x-axis. Now what's going on with this slide? Same two formulas here. Oh, right. I'm just emphasizing that we can connect this with something you may have also encountered in a math class. When you learn the difference between Cartesian and polar coordinates, you're not talking about vectors so much as merely a point in the plane. So you can also think of this vector as specifying a point in the plane. And that point would have an x-coordinate and a y-coordinate. Or you could say it's got a radial coordinate, that's how far it is from the origin, and an angular coordinate, often called the polar angle. So in a sense, the magnitude of our vector is really the polar radius from the origin to the point specified by that vector. Now, I don't want to rely too much on this language of radius, because it's not necessary for this vector to be a position vector. It's not usually, actually, in this class when we use vectors, it's not to specify the location of something. It's to talk about some other physical quantity like a displacement or a force or a velocity, etc. So that's why you don't normally hear the terms, polar coordinates when applied to a vector. But I'm trying to make that connection because you already know about converting between x and y and r theta, which is exactly what we're doing. So that would be the polar radial coordinate or component, the length of the vector, and then of course the polar angle. So what we've done really just now is to convert from polar coordinates, that's the magnitude of the vector and the angle it makes with the positive x-axis, we've converted from those coordinates to rectangular coordinates. And I put this notation here because a lot of calculators, I have a couple $10 Casio scientific calculators that actually have a button with this on it, because you can enter the two polar components, hit a button a couple times, and it will automatically convert to rectangular. So it's worth learning how to use the button on that button on your calculator. But honestly, to me, it doesn't seem any easier than just using the sine and cosine function. The amount of number punching is about the same. How do we do the opposite? Can we go from rectangular to polar? Suppose we know a sub x and a sub y for a vector A. Can we turn those back into the magnitude and polar angle? Well, what kind of triangle is this? Since the components are perpendicular by design, we know this is a right triangle, and we're all familiar with the Pythagorean theorem, or as it's sometimes called, the Theorem of Pythagoras. And we know that that says, if you'd like to know the length of the hypotenuse, just take the sum of the squares of the components and take the square root, right? Remember the old c equals root a squared plus b squared. That's what we're talking about here. So there's nothing new to memorize here. As long as you know the Pythagorean theorem, you will understand that the length of a vector is merely the, sometimes it's called the Pythagorean sum of the components. You could also say that we're adding these components in quadrature. If you think back to the video about error analysis, to add two quantities in quadrature means, I just realized the typesetting's wonky here. What's with this exponent? To add the components in quadrature, you would square the components, then add them up, and then take the square root. It's just Pythagorean theorem. Now, we also know, here's the third trig function that we haven't used yet. If we look at the tangent of this angle, the definition of the tangent of an angle in a right triangle is the opposite side divided by the adjacent side. Of course, it includes sine. Now, in this case, the angle's in the first quadrant, the y-coordinate is positive, the x-coordinate or component is positive. So we're taking the ratio of two positive numbers, and the tangent function takes on a positive value there. Remember, just like sine and cosine, tangent is a ratio of two quantities. Now, we're not interested so much in the tangent of the angle. We actually want the angle, right? We'd like to know what that angle is in terms of a sub y and a sub x. So in order to get at theta, we need to undo this tangent function. So if you apply the inverse tangent function to both sides, also called the arctangent. What's the inverse tangent of the tangent of an angle? It's the angle. It's like saying f inverse of f of x is x. So let's apply the inverse tangent function to both sides. And on the left side, we're left with just the angle theta a, which is what we wanted. And on the right side, we have the inverse tangent, also known as the arctangent of that ratio. So I should emphasize tangent and inverse tangent. When you use those functions, what do you plug into the tangent function? The tangent function is something to which you feed in an angle. You give it an angle and it spits out just a number, a ratio. Like you plug the number 30 into the tangent function and you would get out a ratio. The inverse tangent does the opposite. You give it the ratio and you ask, hey, inverse tangent function on my calculator, which angle has a tangent equal to this number? So you're giving it a ratio and you're asking for an angle. Maybe that's the best way to summarize it. Anytime you use the arctangent function, you are asking for an angle in return. You're saying what angle has this number as its tangent. But there's a caveat there, which I'm going to emphasize repeatedly here. You must check your quadrant because tangent is what we call, let me back up. The inverse tangent is what we call a multi-valued function. I'll make more sense out of that coming up soon here. But let's remind ourselves how the tangent function works as far as signs. Remember, ASTC. The T over here tells you that only the tangent function is positive in this quadrant. Sine and cosine are both negative. So the tangent function is positive in quadrant 3 and quadrant 1. You can remember that because keep in mind, if our angle is this angle right here, theta, tangent is opposite over adjacent. So you're really taking the ratio of the y and x coordinates. In this coordinate, or excuse me, in this quadrant, the x coordinate is negative. I'm talking about this point right here. The x coordinate of that point is negative. The y coordinate of that point is positive. So when you take the ratio of a positive and a negative number, you get a negative number. Hence, the tangent is negative. Down here, both of the components would be negative. The ratio of two negative numbers is positive. Okay? So you want to memorize tangents positive in these two quadrants. Let's look at an example where the angle is in quadrant 4. Now, it's a little ambiguous here. I wrote the number 30 because strictly speaking, this angle is 30, but for the purposes of calculating sine and cosine, it's really negative 30, is it not? Because we've swept out clockwise. Now, this is a special triangle. You can use the Pythagorean theorem to show that the lengths of the sides have to obey this ratio. I picked the simplest possible. I could have gone with, well, notice it says the hypotenuse is twice the length of the short side. I could have called this 2, and then this would be 4. I could have called this 10, and this would be 20. You get the idea. I went with the simplest possible numbers just to remind you how this triangle works. The hypotenuse is twice as long as the short side, and the long side is root 3 times as long as the short side. So when we calculate the tangent of this angle, tangent is opposite over adjacent, but you have to take into account the sign. This is really, if we're talking about this point down here, this point would have a y-coordinate of -1 because it's below the x-axis. So -1 over the adjacent side, which is rad 3, and that would be a positive number if you're talking about the x-coordinate of this point. If you plug that into the calculator, you get this in decimal form. So the tangent of -30 is a negative number. We know it's negative, right? Because it's in quadrant 4. But check this out. What about 150 degrees? What if we'd like to know the tangent of 150? Well, remember the business about the reference triangle? Yes, the angle is 150, but for practical purposes, for actually calculating the tangent, you imagine this reference triangle, drop a perpendicular down, and if this is 150, we know that this angle, the supplement, would have to be 30 because they add up to 180. That means we're dealing with another 30, 60, 90 triangle where the sides are in this ratio. So we use this reference triangle to actually compute the tangent. You can imagine using the components of this point. Well, the x component is negative rad 3, and the y component is positive 1. So when it comes time to compute the tangent of 150, you use the reference triangle. You can use the components of this point right here. 1 over negative rad 3, that's also negative 0.57, etc. So this angle has the same tangent as -30. Two angles, two different angles, for which the tangent of the angle is the same. So what happens if you then try to flip it inside out? If you ask your calculator, hey, Mr. Calculator, what is the inverse tangent of negative 0.577, etc.? What angle has a tangent of negative 0.57, etc.? What's the calculator supposed to do? Have you ever asked a question of your calculator like that and your calculator gave you two options? My calculator doesn't give me options. I don't like options anyway. It makes my head hurt. That's why if I go to an ice cream store, I just get chocolate. I don't even look at the other stuff. It's easier that way. And the calculator is the same way. It's going to have to commit to one of these choices. We know that -30 has a tangent of negative 0.5, etc. And we know that 150 also has a tangent equal to that number. So what does the calculator do? Well, there's a convention, or there's a rule that most calculators follow. And I'm emphasizing here that the arctangent of x is a multi-valued function, because when you plug in negative 0.577, etc., there's really an infinite number of possible angles that have that tangent. But this is what we do. We restrict the domain of the original tangent function to these two quadrants. So we just imagine that we're only taking the tangent of numbers like -50 or +50. We don't mess with angles over here. And if that's the case, then we would default to the arctangent of -1 over rad 3 as being -30. Okay, that's it. The calculator just assumes that the angle you're talking about is in quadrant 4. And since positive angles, or since angles in this quadrant always have a positive tangent, and angles in this quadrant always have a negative tangent, if you give the calculator a negative number and ask what is the inverse tangent, it's going to assume you're in this quadrant. If you ask the calculator for the inverse tangent of a positive number, it will assume that your angle is in this quadrant, even though it could really be in this quadrant, right? Tangent is also positive over here. So it's up to you to correct for that. And that's what I mean by check your quadrant. So here's an example. Oh, this is kind of a faux pas. Look what I did here. This is kind of bad. I labeled this angle theta b. Shouldn't have done that, because I'm trying to stick to the convention where I reserve the letter theta specifically for the angle measured from the positive x-axis. It's okay to do it this way, but you would probably want to call that angle something else like phi. So I'm not going to go back and redo these slides, but please observe, this isn't really consistent with the rule I've been using. I'm trying to reserve the letter theta strictly for angles measured from positive x. But let's for now forget about that. Find b. Notice there's no arrow here. So I'm not talking about finding the vector. I'm talking about finding the magnitude of the vector. Let's find basically the hypotenuse of this triangle and this angle theta b. You know what? That's really going to bother me. I think I might have to fix that. Yeah, that's bad. Hang on just a second. Okay, that was a necessary change. Ideally, I would have a little arc here to indicate that theta b is the angle that this vector makes with the positive x-axis. It's this angle right here. And we'd like to find that angle in addition to the length of the vector b. Well, the length of the vector is easy. Again, it's just Pythagorean theorem. This is true for any vector for which you know the rectangular components or Cartesian components. You just take the square root of the sum of the squares. And notice it doesn't really matter if you include the sign -5. Strictly speaking, this is a negative x component. When you square a negative number, the minus sign goes away anyway. And I'm just using this fact. This is really a 45, 90 triangle, is it not? And so the hypotenuse has to be √2 times one of the sides. So that's easy. Getting the length is easy. Now, there's probably a button on your calculator that will also convert. Yeah, that's part of the rectangular to polar. Again, it's not really necessary. I would just get quick at typing in b sub x, hit the square button, plus type in b sub y, hit the square button, hit equals, and then hit the square root button. Okay, now what about theta b? If we just naively take the arctangent of the y component over the x component, because that's your starting point, just take, on my calculator, I would say 5 divided by -5, I would hit equals, and then I would hit the arctangent button. So that's really taking the arctangent of -1. Notice how the ratio is -1. So what is the inverse tangent of -1? What angle has a tangent equal to 1? You probably, or I should say to -1. Hopefully you're thinking that would be -45. Here's a 45, 90 triangle where the opposite side and the adjacent side have the same length, but because the y coordinate of this point is a negative number, we're really taking -1 over 1. So your calculator will in fact spit out this number. It will assume that the angle you're talking about is in quadrant 4. But we know it's not in quadrant 4. We can just look at the picture. Since we know what the x and y coordinates are, or components, we know which quadrant this vector actually lies in. So it's up to us to correct the answer that the calculator gives us. How do we go from -45 to here? Well, do you see the relation? This is a line, right? This vector from here to here and the vector b from here to here, they're 180 degrees apart. So it's up to us to add 180, positive 180, to the angle given by the calculator. So really, it amounts to this. If you know the x and y components of your vector, then you will know which quadrant you're actually in. The calculator is going to give you an answer either in quadrant 4 or quadrant 1. It's up to you to add 180 to correct that angle if necessary. For instance, what if your vector was over here? We know that the tangent function is also positive over here. If you took the arctangent of the ratio of your two components and the calculator told you that your angle was in quadrant 1, again, it would be up to you to add 180. That's really what I'm saying, or what I mean by check your quadrant. So the actual angle theta b would be 135, which is 180 degrees greater than -45. Now, you may be aware that, like, you're probably thinking, this is just pesky. What if you want to do this in an automated fashion? If you're doing calculations in a spreadsheet or using a program like Mathematica or MATLAB, there are some native functions that account for this. Notice when we use the arctangent function on our scientific calculators, we're really just plugging in one number. 5 divided by -5, you may be hitting 5 divided by -5, but once you hit the equal sign there, that's just a single number. So there's only one argument that you give to the inverse tangent function. And that's why your calculator doesn't really know if you're in quadrant 3 or, quadrant 2 or quadrant 4. Because your calculator doesn't know the components, the two components, when you just give it a single ratio. However, I think it's called atan2 in MATLAB. You can look this up on the web, but a lot of these programs have a special function that will account for your quadrant, so you don't actually have to check your quadrant. And those functions require you to input the x component and the y component separated by a comma. And so the calculator in that case actually knows both of those pieces of information, and it can figure out for you which quadrant you're in. So to summarize, here are the two formulas that allow you to convert from rectangular components back into what you might call polar components. In this case, or in this context, maybe it makes more sense just to say the magnitude of the vector and the polar angle of the vector. In other words, the angle that the vector makes with the positive x-axis. Don't forget to check your quadrant. And in this case, I've written R to P. You may find that button on your calculator. Again, I don't even know how to use that button. I just use sine and cosine and tangent. So there they are. You will be using this often in the coming chapters. I wouldn't even memorize it so much as just understand it. If you understand it, there's nothing to memorize. Don't forget to check your quadrant. All right, now it's time to actually add vectors using these components. The previous slides all dealt with a single vector and converting its components between rectangular and polar. Here you can see I've placed two vectors tip to tail, which means they're ready to be added graphically. We know that vector A has its own x and y coordinates, and evidently I'm using a coordinate system where the x-axis is horizontal on the screen and the y-axis is vertical. Vector B has its own Cartesian components. Now before I proceed here, maybe you should try to take a guess. Once we add these two vectors, and I will call that sum vector C, once we find the sum of these two vectors, C, how do we get the components of C? You know, what are C sub x and C sub y? Since we know what A sub x and B sub x are, maybe you're thinking we just add them, and we'll see that that is in fact the case. So here is the sum of the two. I've just added them graphically, right? If you place A and B tip to tail, you can close the triangle. That vector is the sum of the two vectors. It's the resultant. And now I've indicated that this vector has its own y component and x component. So I've made a right triangle out of the vector C. And now we can observe, it's pretty self-evident. When you look down here, see how this yellow dotted line is the x component of vector A? This green dotted line is the x component of vector B. If you add this length to the yellow length, don't you just get this total white length at the bottom? So it looks to me like C sub x, the x component of vector C, is indeed the sum of the x components of the two vectors A and B. Simple as that. Let's look at the y component. If I take this green length here and this yellow length, they do sum to the length of the y component. So it's pretty intuitive. If you know the rectangular components of A and B, just sum them up, and now you have the rectangular components of C. So very often what you're doing is you might be given the length of A, the length of B, the angle of A, the angle of B. You may have to use the previous trig functions, you know, A sine theta, A cos theta, to find the y and x components respectively. Same thing with the B vector, but once you've got those rectangular components, you merely add them to find the rectangular components for C. Now once you've got the rectangular components, what if we'd like to know the length of this vector and the angle that this vector makes with the x-axis? Again, we go from Cartesian back to polar using the Pythagorean theorem and the arctangent function. So it's just the same procedure repeated. You're going one way or the other. You're either plugging your Cartesian components in to find polar or vice versa. And once you've gotten some practice with this, it'll be second nature. Oh yeah, don't forget to check your quadrant. So let's move on to an example on paper. So while this is not an assignment, I highly encourage you to give this a shot on your own. You'll need a ruler and a protractor. This is just an example of adding two vectors graphically and what you might call algebraically, and confirming that you get the same result using both methods. So let me just choose two vectors, and instead of writing the Cartesian components in parentheses, let's do what your book likes to do. They will very often write a vector in its polar components. They'll specify the length of the vector and then the direction that it points. Now, the direction could be something like 30 degrees, where it's understood 30 degrees from the positive x-axis, or they might say something like northeast. So sometimes they're descriptive in that way. How about something like 140 meters is the length of my vector at an angle of 60 degrees. And then I'll take a second vector, also specified using its polar components. We'll go with 220, measured at, let's go with the much larger angle, or larger angle, something like 110. And now we'd like to find the angle C in terms of its magnitude and the angle, the conventional angle that it makes with the positive x-axis. I'll do this two ways. First, I'll do it graphically using the tip-to-tail vector addition that we looked at. Now, I'm going to draw this picture on this piece of paper. 140 meters. Is that going to fit on this sheet of paper? This piece of paper is not even 1 meter across. So the first thing we'll have to do is choose a scale factor. Since I'll be using a metric ruler here, I have to pick my scale factor, like 1 centimeter from 4 to 5. How much distance will that represent? Well, I've got about 30 centimeters to work with on the ruler, but I don't want to get ahead of myself. I'm drawing this on this sheet of paper, and even the greatest distance on the, okay, it's about 30 centimeters. So where's my calculator? Let me grab a calculator. Well, the longest vector is 210. So if I wanted to use the diagonal of this paper to represent a 220 meter vector, 220 meters divided by 30 centimeters would mean I would need each centimeter to represent about 7 meters. That seems confusing, right? Because a centimeter is, of course, not 7 meters. But we're just talking about a scale factor here. But it's not good enough just to use that, because I'm actually adding these two vectors. I'm going to have one vector going off like this and the other vector going off like that. And I have to be able to fit all three vectors, the two input vectors and their sum, on the same sheet of paper. So maybe it would be easier or safer, instead of 7 meters per centimeter, I'm going to go with something like, let 1 centimeter equal 20 meters. So this is 1 centimeter on the paper. And that means, again, this is probably the only context in which this would make sense. 1 centimeter compared to 20 meters. In this case, I'm setting that equal to 1. That's how a conversion factor works. Let this ratio be equal to the number 1 so that I can multiply by this ratio. And I won't be changing a quantity, I'll be converting it. That'll make more sense when you see me actually do it here. Okay, well, since I know one of the vectors goes off at 60 and the other one goes off at 110, I'm thinking I can start over here. I'll put the origin right there, and I'll draw the positive x-axis. And obviously you have to use a straight edge for this. Otherwise you're not really making it, you're not doing any math, you're just kind of sketching without the straight edge. There's my x-axis. And now it's time to draw my vector A. Well, my vector A makes an angle of 60 degrees with the positive x-axis. So at least for this protractor, and if you don't have a protractor, you could actually go online and print one out. And the one that you print, of course, isn't going to work the same way, but I need to put, there's a little hole here, and that hole is at the, it's on some crosshairs. I put the crosshairs at the origin, and see the black line here? Not the bottom. This is an easy mistake to make. So I'm not talking about the bottom of the protractor, the bottom edge. I'm actually talking about this black line that passes through the dot, or the hole. That black line is what needs to align with the positive x-axis. Right, so they seem to be overlapping pretty well there. And I want my vector A to go off at 60 degrees. So you've got some numbers on the top that have values like 140, 150. That's too large. So obviously we're going to use these numbers on the bottom here. There is the notch for 60. See, 60. And I'll put a dot right here. And that will determine the direction of A. And you know what I'm already realizing? This was silly of me. If I draw my vector off in that direction and put a dot there, I probably won't have room to draw B. Oops. So why don't I start from here instead? Maybe this will give me room. And I may still run out of room, in which case I'd have to start over. But if I put my origin there, mark off 60 degrees. Okay, so I need to draw a ray from the origin through that point, and that'll be the direction of vector A. Well, how long should A be? Not the letter B. How long does vector A need to be? It's 140 meters. So 140 meters times, let's use our scale factor, 1 centimeter for every, what did I say, 20 meters? And I picked easy numbers on purpose. That would be 7 centimeters. So on the page, we're going to represent that 140 meter vector with a vector that's drawn 7 meters long. Okay. Excuse me, 7 centimeters long. Now, usually I like to draw an actual line, but 7 centimeters doesn't even reach to the dot. So I'll just put my ruler, and I'm making sure that the 0 centimeter notch is on the origin, and the ruler needs to pass through, the edge of the ruler needs to pass through the dot that I just drew. And actually, this is the end of the vector. And the finer the point of your pen, the better your results will come out. Because a thicker line actually amounts to greater angular error. So here's the vector A. Put an arrow. And I guess I can label this now 7 centimeters. Now, do I want to label it in the actual physical dimensions or physical units of centimeters, or label it as 140? I think I'll go ahead and label it as 7 centimeters. And I'll call this angle 60. Okay, now the next vector. Remember, if I want to do this graphically, I have to place them tip to tail. Vector B is this long, and it goes off at 110. Well, 110 from what? It's 110 from the positive x-axis. So I need a vector that starts here, because I'm going to put them tip to tail, and it needs to go off at 110 from this axis, which is somewhere over here. So I could just try to eyeball a line here that's parallel to the x-axis. And I can try to sketch a line parallel to the x-axis, and then put my protractor there now so that the hole lines up with the tip of vector A, and repeat that procedure, this time marking off 110. What's the problem with that, though? I'm just using my eyes to judge that this line is parallel to this one, and that means that I'm introducing error. So what would be better is to extend vector A. It's almost like you're making a new axis. And if I want to draw vector B, let me give you a picture to work with before I actually do this. Let's see here. If this is vector A, and this is vector B, for instance, A, my x-axis goes off in this direction. Oops. So I could call this theta A. This angle from vector B down to the x-axis, that's theta B. What about this angle? How would you get the angle between vectors A and vector B? If we know that this angle is theta B and this angle is theta A, isn't this theta B minus theta A? You see that? Theta B minus theta A. So I can go back to my drawing that I was working on and actually use this angle to precisely draw the angle between the two vectors, theta B minus theta A. And this will work even if this comes out negative. Like what if you're subtracting, what if theta A was the larger angle, and I have to change this picture, but like 80 minus 110 would give you a negative angle. Everything that I'm about to do will still work out even if theta A is the larger angle. Okay, where's my drawing? This piece of paper? Okay. So if I want to draw theta B now, I'll have it coming out of this point, but the angle that it makes with this axis will be theta B minus theta A. So up here I'll say theta B minus theta A, that's 110 degrees minus 60 degrees, which is 50 degrees. So the angle that I really need to draw is 50 degrees from the direction of theta A, right? Think about B and A both emanating from the origin. So here's A, here's B. If I slide B up, vectors are scootable, right? So I scoot vector B over, it still makes the same angle with this line that it makes with vector A, because this line is in the direction of vector A. So let me now mark off a 50-degree angle. I'll put the hole on the tip of vector A, make sure that the black line lines up with the extension of A that I just drew, and here's a dot for 50. So I need a ray going from here through that dot. You can't even see that dot, can you? I was trying to make it small to minimize error. And this vector needs to have the length we've specified. So for vector B, I chose 220 meters. Okay, well, 220 meters times our conversion factor. I'm using 1 centimeter to represent 20 meters. The zeros cancel. What is that, 11? 22 divided by 2? 11 centimeters. Okay, so using my ruler, I put the 0 notch at the tip of vector A, and I make sure the edge of the ruler passes through that dot, and I mark off a dot for 11 centimeters. And that is where vector B will end. Okay, and I can label this, what do I want to label this? 11 centimeters. And this angle, of course, is 50. And it's kind of nice to put the scale factor on your drawing so anybody looking at it knows what you've done. I could say 1 centimeter means, I've already forgotten. How many meters was that? 20, right? What are we doing? Remember, I'm adding these vectors graphically. So now it's time to close the triangle. This is the easy part. Okay? And if I call this vector A and this vector B, remember I was calling this vector C. It's the sum of A and B. And it's kind of a coincidence. I didn't intend for this, but that vector C almost points straight up. So the angle that it makes with the x-axis, excuse me, is going to be close to 90 degrees. It won't be exact. Let's first determine its length. Now, ultimately, since we've specified A and B in meters, we'd like to know the length of vector C in meters, since it's the sum of A and B. What I can do is measure it in centimeters and then convert again. I'll do the reciprocal of the previous conversion factor to go back to the actual meters, or the dimension of meters. I should say units of meters. I think dimensionality just means, is it a length, is it a time? So the dimensionality is distance, and the units are meters. Okay. I will put the 0 right at the tip of vector C. And it looks to me, it's kind of difficult to do this with the camera stand in the way, and by camera stand I mean, oh, that was my head. I mean the floor lamp that I'm using. What is that, 16.8 Tough to see there. And 16.3, I'll call it, centimeters. Okay, now let's convert. I'll just do it right here on this page. 16.3 centimeters times, now be careful, previously I wrote 1 centimeter for every 20 meters. Well, I want the centimeters to cancel now, so I need to put the 1 centimeter in the denominator and the 20 meters up top. Makes sense, right? If every centimeter represents 20 meters, then you would just take the number of centimeters and multiply by 20. Can I do that in my head? 16 times 2 is 32. 0.3 times 2 is 0.6, so I think it's 32.6, and then I'd have to move the decimal point over 1. 32, so is that 326 meters? I better check. Okay, 326 meters. And for the angle, theta sub c, I should probably emphasize that is the length of vector c. And for the angle, I will measure it with the protractor. So everything I'm doing right now is graphical method. I haven't used sine or cosine, no trig functions. This is the first method that we looked at. Okay, to measure that angle, again, I will put the hole of the protractor at the origin, and I'll make sure that the black line lines up with my x-axis. And this is really watching this video is no substitute for doing this yourself. Try to find the time to go through this exercise, because it'll really cement in your mind the connection between this graphical method and the second method, which we're about to do. Okay, now, I can't zoom in, but if you were here in person and you were looking really carefully, you would probably agree with me that this is between the 91 degree mark and the 92 degree mark. See the line here? It passes through a point that's a little past 90 degrees. So I'm going to call that 91.5 degrees. And clearly there's some error involved there, right? I don't really know that it's 0.5. It could be 0.6, 0.8 even. If we used a really fine pencil and we were super careful with our protractor and our ruler, maybe we could do better than that, but honestly, probably not. You'd have to do that on a computer or like a big drafting table with precision instruments. That sounds kind of rewarding, but I don't have that stuff. Okay, let's check now. Let's do the other method. We will take the polar components of A and B, which are given, convert those into Cartesian components, manipulate the Cartesian components to find the Cartesian components of C, and then lastly convert from the Cartesian components of C back into the polar components and see if those polar components agree with what we already know from the picture. That should be gratifying if everything works out. So let's kill another tree here. They grow back, it's fine. Hey, climate change. If it gets hotter, shouldn't the trees just grow better anyway? I don't know. I'm no expert on that subject. It's super complicated. You think physics is difficult? I can't even imagine climatology. What a crazy large system with so many variables. That's got to be a very challenging subject. Okay. A sub x. Let's immediately calculate the x and y components using our formula. You just take the hypotenuse and multiply by, which trig function is it? As long as you've measured your angles from the positive x-axis, and by assumption, that's what these angles do, you can always just multiply by the cosine of vector A's angle, and that will give you the x component. It works every time, provided your angle is defined as I just described. So that would be the 140 meters times the cosine of 60, and I actually know that ratio. Cosine of 60 is the same as the sine of 30. See how that works? 60 plus 30 is 90. Cosine 60 equals sine 30, and I happen to know that the sine of 130, excuse me, the sine of 30 degrees is 1/2, so this is just 70. All right. Does that make sense with our picture? You know, if we were to imagine the dotted line components here, 70 this way, and then we're going to find this distance, that would equal the total 140. Okay. And the y component, we take the hypotenuse of A times the sine of vector A's angle. That's 140 meters times the sine of 60. And that one is not so simple. Sine of 60 is the 1 over rad 3, I believe, which I think is like 0.866. But let's just do it in the calculator. On my calculator, I hit the angle first, 60 degrees, then I hit the sine, and I take that and multiply by 140. 121.2, I'll say. Let me keep a few extra digits for now. In fact, I'm going to store that in memory so I don't have any rounding error. It's not that important because there's obviously error involved in this method, but I want to maximize my chances of getting these two results to agree. So memory input. And now it's time to convert these Cartesian components, which we know, into polar. No, we don't need to do that. Yeah, let me step back. We don't need the polar components of A. We're already given those. We need to add the x and y components of A and B to get the x and y components of C. That's what we're doing. Okay, so the x component of vector B is the length of B times the cosine of theta B. Remember, you can always use this provided that theta is measured from the positive x-axis. Presumably it is. So that's 220 meters times the cosine of 110 degrees. 110 cosine times 220. So I didn't actually need that number that I put into memory. Let me just keep a few digits. Negative 75.24. Now, does that make sense that it's a negative number? Let's look at the picture. Yeah, vector B points in that direction. So its x component would in fact be negative. Does it seem reasonable? If the length is 220, then what would this component be? That sounds about right. 75 long. The y component we expect to be positive. We multiply the hypotenuse times the sine of theta b. I find this kind of relaxing, don't you? Just plug in numbers. Let's see here. 110 degrees sine function times 220 meters, and I get 206.73 meters. All right, most of the work is done. Well, half the work is done. Now we know the x component of vector C. Since vector C is the sum of vectors A and B, then the x component of C is the sum of the x components of A and B. So that's 70 meters for A and negative 75 for B. And notice I put the units on the outside. I'm trying to be didactic here, but when you're doing this on your own, you probably aren't going to write all the units. It's not necessary. If you were turning something in for a lab report, you would want to include units. And on your exam, you would want to include units, especially at the end. At least at the end, maybe not throughout the calculation. 70 minus 75.24. Guess I could have done that in my head. Negative 5.24. So that's a very small x component. Does that seem reasonable? Yeah, I mean, I'm not even going to attempt it here, but this vector is tilted ever so slightly from the vertical. So it does have a very small x component in that direction and a much larger y component. Let's find that y component. It's the sum of the y components. I think you get the idea here. 121.24 plus 206.73 meters. I probably don't need to keep that many decimal places. One would be sufficient. 27.97 meters. All right. Now I've got my x and y components. That's a 2 right there, 327. It's time to convert back into my polar components. We've got the rectangular components. We would like to confirm that vector C actually does have a length of about 326 meters and that it makes an angle of 91.5 degrees with the positive x-axis. Okay. Here we go. The magnitude of c, we use the Pythagorean Theorem. We take cx, square it, c sub y, square it, add them up, take the square root. And I'll just do all that at once. I won't even worry about the minus sign because I'm squaring everything. So 5.24 squared, that's the x component squared, plus 327.97 squared, it equals, then I take the square root, 328. And it says 328.01, let's just round, 328 meters. Awesome, because that's pretty close to the 326 that I got from the graphical method. All right, 328 versus 326. The difference between those is 2 meters. Well, how does 2 meters compare to either one? I'll go with 327 because that's halfway between the two results. 2 meters compared to 327 meters. 6 times 10 to the negative third. If I multiply by 100 to convert that into a percentage, 0.6. That's less than 1%. So I was careful enough that my two results for the length of vector c are within 1% of each other. Cool. I'm sure I could do a little better if I had a bigger sheet of paper and a real fine pen point and I was a little more careful. What about theta sub c? Well, we take the arctangent, the inverse tangent, and I should point out, inverse tangent of some number is not the same as the reciprocal of tangent. That's an easy mistake to make when you're first starting out here. This does not mean tangent of x to the negative 1 power. Not at all. It does not mean that at all. It means inverse function. There's a name for the reciprocal of tangent. We call that the cotangent. So please don't make that mistake. Inverse tangent has nothing to do with, literally nothing to do with the cotangent function. Okay, inverse tangent of cy over cx, with the understanding you're supposed to check your quadrant here, right? What quadrant do we know c is in? We've got the x and y components. We know that the x component is negative, so vector c points this way a little bit and this way. It's in quadrant 2. Now, what is the sign, sign, of the tangent function in quadrant 2? ASTC. Tangent is negative in quadrant 2. So we know that we're asking the calculator for the arctangent of a negative number. Arctangent in your calculator will always assume that your negative ratio comes from an angle in quadrant 4. So it's going to think that we're somewhere over here. It's up to us to correct, to add 180 degrees so that we're actually looking at an angle in quadrant 2, not in quadrant 4. So let's do this. I'll say, let me put an arrow instead of an equal sign. So I'm going to say this goes to the arctangent of, what do I have here? 327.97. Again, I don't really need all those digits. Divided by negative 5.24. And I, with the benefit of foresight, or is it hindsight? I don't know. I know that I need to add 180 degrees. So I guess when I write arctangent of this, by this function I really mean the output from the calculator, not the actual angle we're talking about. So on my calculator, I would do 327.97 divided by 5.24 with the minus sign. I hit equals first, so I compute that ratio. I'm really asking the calculator, hey, what angle has a tangent of negative 62.6, let's say? And the calculator assumes that I'm in quadrant 4, and it tells me that the angle is negative 89. What? Negative 89, that would put C here. Well, we know that the sum of the two vectors doesn't point in that direction. It's up to me to add 180. So plus 180, 90.9 degrees. Okay, so the agreement in this case between the algebraic method and the graphical method was not as good, because for my graphical method I got 91.5. Here I'm getting 90.9. Can't we just round this to 91? So the difference is half a degree, more or less. And half a degree compared to the answer of 91 degrees multiplied by 100. I don't think I did that right. Half a degree. No, I did do that right. Half a degree divided by 90. Yeah. Still less than 1% error. Okay, I guess it did come out comparably. That's interesting that both the length of vector C and the angle were in error from about, or maybe I should say there was a discrepancy of about 0.5% for both of those between the algebraic method and the graphical method. But that should be enough to convince you that this works, right? Both methods are consistent. You can add angles graphically, or you can add them, excuse me, I should say, you can add vectors graphically, or you can use the trig functions. Highly encourage you to try this on your own, and you might try doing the following. When you sit down to do it, make this angle perhaps smaller, than this angle, which will force you to really think about how you're supposed to draw that second vector with the protractor. I'll give you a hint. You're probably going to have to flip your protractor around and put it on the other side of this line. Where's my protractor? I just pointed, as I was going through this, I showed you that when it comes time to draw vector B, you have to draw, or take the difference between the two angles, put your protractor like this. If you find that the difference comes out negative, since you're going theta B minus theta A, if theta A is a larger number, you'll get a negative number for the difference. That means you'd have to do your protractor like this. Okay? And there was one other thing I wanted to say about that, and now it escapes me. I suppose I'll have to save that for another time. Oh, yeah. So, you may have also thought, okay, well, since we ended up just rotating our protractor, putting it like this, why not just dispense with the angle 60 and just put our x-axis there? You could actually do that. You would still arrive at the same answer for the length of B. You could have just said, okay, let's just decide to put vector A along the x-axis. Basically rotate your coordinate system. So now the x-axis points along A, and then vector B would go off at an angle equal to, it's really sloppy, equal to theta B minus theta A equals 50 in this particular example. And then you would close the triangle and proceed as before. You'd still get the same answer for the length of vector C. The only difficulty with that is you would have to measure this angle, which is really theta C minus theta A. And then you'd have to add that to theta A to get the angle ultimately the vector C makes with the x-axis. So maybe it's actually easier to do it the way I did it. All right, have fun with that.